So let's continue our discussion about vertical asymptotes, and I've got three new rational functions here, and we're prompted to, well, what are the vertical asymptotes for the following functions? So we just want to find out what their vertical asymptotes are. Not graphing, just locating those asymptotes. But it says to state your answer in the form of vertical line equations. Remember, vertical asymptotes are going to be those vertical lines where the graph won't cross, where it goes to positive or negative infinity on one side, like the graphs we just looked at a little while ago in the last video. So since they are vertical lines, you need to state your answer for a vertical asymptote as x equals 4 or x equals -5 or something like that. So remember, your vertical asymptotes come directly from the domain exclusions. You should always locate those exclusions first before listing the asymptotes. So domain exclusions for these functions come from your denominator. I need to guarantee the denominator is never equal to 0. So in this case, I'll factor this denominator. That'll factor as x minus 3 times x plus 2. So that means your exclusions would be x equals 3 and x equals -2. Well, that also means your vertical asymptotes occur at x equals 3 and x equals -2. So vertical asymptotes are always in the form of vertical line equations like this, and they come directly from those exclusions. See, the excluded values would be x can't equal 3 and x can't equal -2. So whatever your domain excluded values are, those default to being the vertical asymptote vertical line equations. Okay. For example B, g of x equals x plus 5 over x squared plus 9. Now, x squared plus 9 is a sum of two squares. It's not a difference of squares, so I can't factor it. And if you recall from this example on the first page, anytime you have x squared plus a value, like this one, x squared plus 9, remember, there are no values of x that you can plug into this denominator to cause division by 0. So, no exclusions here. Means that this graph has no vertical asymptotes. So forgive my abbreviation, but that's exactly what it means. If there are no exclusions, you have no vertical asymptotes. So this one will have a connected continuous graph everywhere. This last one, I guess I actually saved the easiest one for last. This k of x is x squared minus 9 over x plus 2. So, because you have division and you have a denominator that does potentially go to 0, you've got to guarantee you exclude that x equals -2, and that means you're going to have a vertical asymptote at x equals -2. So of these three, the only ones that have vertical asymptotes are f of x and k of x. G of x has that denominator that never turns to 0, that x squared plus 9. So, locating vertical asymptotes is the first essential skill you need in order to make a graph of a rational function. Now, the second thing is the end behavior of the rational function's graph. You're going to probably want to take a screen capture of this right here. This is going to take some studying. This is going to take you making at least 3 note cards to commit these facts into memory. Okay. What the other graph attribute you're going to need, in addition to the vertical asymptotes, is to see what kind of end behavior, what the left and right ends of the rational function's graph are actually going to look like. So that comes from, well, knowing this information in this chart. The behavior for the extreme left and right portions of a rational function's graph are influenced by the degree in your numerator's polynomial and the degree in your denominator polynomial. Remember, the generic form of a rational function is the quotient of two polynomials. So, what you need to do is note the degree of those two polynomials. Okay? Remember, the degree represents the highest exponent. So, let's see in these examples up here at the top of the page, the degree of the numerator is 2, the degree of the denominator is 2. That combination of degrees will cause one particular type of end behavior for this rational function's graph. This one's different. the numerator and the denominator have a different degree. The numerator has degree 1, the denominator has degree 2. So if the denominator has a bigger degree, then that causes one particular type of behavior. And in this one, it's flipped. You have a degree 2 polynomial in the numerator, degree 1 polynomial in the denominator. If the top has a bigger degree than the bottom, that'll make a different influence on the graph. So there are like 3 case scenarios to look at, depending on what your degrees are for the top and the bottom polynomials in the fraction. So if the numerator degree is less than the denominator's degree, what's going to happen is the end behavior of the graph gets closer to the value y equals 0. In other words, the graph will use the x-axis as a horizontal asymptote. See, the word asymptote is always going to be used to reference a line of some sort where a graph keeps getting closer and closer to without ever usually touching it or crossing it, or to sort of format the shape of the graph as it approaches or gets close to that asymptote. See, of these 3, the numerator's degree is less than the denominator's degree. That's going to give you the x-axis as a horizontal asymptote. Now, in the second scenario, you have a different case if the numerator and denominator have the same degree. If you have the same degree in the top and the bottom, you still have a horizontal asymptote, but it's not going to be y equals 0. It's going to be y equals this constant. This end behavior is going to be dictated by the leading coefficient of your numerator divided by the leading coefficient of your denominator, and still makes a horizontal asymptote. So in both of these first 2 cases, a smaller degree in the top of the fraction or the same degree in top and bottom, you'll have horizontal end behavior. But you can also have slanted or tilted end behavior in this third case. If the numerator's degree is greater than the denominator's degree, your end behavior will be a slanted asymptote. And to find the equation of that slanted asymptote, you can use synthetic or long division on the rational function. And this is the important part. Again, you need to make note cards for all 3 of these. This is intense, study-worthy stuff right here. To get that slanted, tilted line equation, what you do is the equation of the slanted asymptote is determined by the quotient of your division. You actually ignore the remainder. So you have y equals 0 in this first case as your horizontal asymptote. Y equals lead coefficient numerator divided by lead coefficient denominator is this horizontal asymptote. And then you have, in this case, you have an actual y equals mx plus b, a slanted line, as your asymptote. And it's going to be y equals the quotient based on whatever your division is. So let me show you some examples of these. Again, take a screenshot of this. Commit this to solid memory, because this is probably the most, I won't say it's confusing, but it's one thing you definitely have to get some essential practice on to make sure you're clear on which of the 3 case scenarios you've got. So on the next page, I want us to determine the end behavior for each of these rational functions. State your answer in the form of a horizontal lines equation or a slanted lines equation. And remember, a horizontal lines equation is always going to be y equals some constant. A slanted lines equation could be in the form of y equals mx plus b, if it actually has a proper slant or tilt to it. Okay. So each of these examples exemplify those 3 case scenarios from the previous set of notes. Remember, the end behavior is determined by comparing the degree of the numerator and the denominator. So that's the first thing you want to note. The degree of my numerator equals 1. The degree of my denominator also equals 1. So of our 3 case scenarios from this previous page, the numerator's degree is the same as the denominator's degree. Whenever they have the same degree up top and bottom, your end behavior is going to be in the form of y equals lead coefficient numerator divided by lead coefficient denominator. Same degree up top and bottom. They have equal degrees. The end behavior will be y equals the ratio of those leading coefficients. So in this case, we will have a horizontal asymptote at y equals, the lead coefficient is the coefficient on that highest x. So the lead coefficient of my numerator is 2. The lead coefficient of my denominator is 1. So our horizontal asymptote is going to be y equals 2. And I usually abbreviate horizontal asymptote as HA, just for the sake of abbreviation. Okay? So whatever this graph looks like, the further you go to the left and right, it's going to get closer and closer to the graph of y equals 2. Let me show you what that looks like. Clear this old one out. Okay. So we're graphing f of x equals 2x minus 1 divided by x plus 3. Okay. So then graph this in zoom standard. So we already know the vertical asymptote occurs at x equals -3. So our vertical asymptote is still the same. There's that vertical line where the graph goes to positive infinity on the left, and in this case it comes from minus infinity on the right. But now we're talking about the end behaviors of the graph. What happens as you go further to the left and further to the right on this graph? And according to this, the graph kind of levels off. If a graph has horizontal asymptote behavior, that means the graph actually levels off and gets closer to that horizontal asymptote the further it goes left and right. So you can kind of see a little bit of that here. If I overlap the graph of y equals 2, it'll graph in red, if you can see that. Okay, refocus this, and then overlap those graphs. So see, there's the graph of the line y equals 2, and that's what it means for it to dictate the end behavior of the graph. The horizontal asymptote doesn't take any influence in here in the middle. You know, the main influence in here is that vertical asymptote at x equals -3. The further you go to the right and to the left is where the y equals 2 is going to take its major influence. So if I zoom out one step further, zoom number 3, zoom out, and I'll zoom out from the origin and hit enter. So see, the graph starts off looking like a horizontal line, and then it makes its vertical asymptote jump, comes from minus infinity on the other end of the vertical asymptote, and then kind of levels off. So the further you zoom out, the extreme left end of the graph and the extreme right end of the graph look like they almost become that horizontal line y equals 2. That's why you need to know how to find that horizontal asymptote, because it does dictate the end behavior of the graph. And shows you, what the graph sort of levels off to as you go to the left and right ends of the end behavior. Okay, let's try this next one. This function g of x is defined as x plus 1 over x squared minus 16. So you start off by comparing the degrees. The degree of my numerator is 1. The degree of my denominator is 2. So, of our criteria, the numerator's degree is 1, the denominator's degree is 2. So, in this case, the numerator's degree is less than the denominator's degree. So we're back in case number 1 here. And it's frankly the easiest case. If you have a smaller degree up top than you have in the bottom, then the end behavior is going to be y equals 0. So degree 1 over degree 2, smaller degree up top than I have in the bottom. The end behavior will be a horizontal asymptote at y equals 0, which is again just the x-axis. X-axis. Okay. So let me show you that one. This function x plus 1 over x squared minus 16, so parentheses around x plus 1 over x squared minus 16, zoom standard. Yeah, notice the graph starts off looking like it's really close to the x-axis, and then it has a vertical it's got two vertical asymptotes. Well, the denominator is x squared minus 16. That makes for two exclusions, -4 and +4. So the horizontal asymptote behavior kicks in on the left and the right. It's the left and right end behavior. So on the left, the graph is very close to the x-axis, and then it makes its vertical asymptote jump. On the right, the graph is close to the x-axis, but notice the graph actually crosses the x-axis here at the origin. I mean, it has to, This part right here is continuous, and it comes from positive infinity, crosses the x-axis to minus infinity. So there's the difference. The graph can never cross a vertical asymptote under any circumstances. They will always be an invisible wall that causes this positive and negative infinity jump behavior. But your horizontal asymptotes, like this one from example A or this one from example B, they really only take their influence on the extreme left and right ends of the graph. They don't have much of an influence here on the graph at all. That's why they're dictating the end behavior. So the further you zoom out, this graph of g of x will get closer to the x-axis on this left side and this right side. The end behavior only is what that horizontal asymptote tells you. All right. And this third one, compare the degrees here. The degree of my numerator is 2. The degree of my denominator is 1. So, in this case, the numerator's degree is larger than the denominator's degree. The end behavior will be slanted. It will be a line like y equals mx plus b. It says use long division, but you can use long or synthetic, whichever is most practical. You actually do the division that's inherent to the rational function's definition. So, I want to divide. I want to divide x squared minus 9 by x plus 2. I mean, keep in mind, when you see these big fraction bars right here, that fraction bar is the same thing as that division symbol. So if I actually carry through this division, and here's a case where you can do synthetic division. So if I turn this into a division problem, my synthetic divisor will be negative 2 from x plus 2. I'm dividing it into 1x squared plus 0x minus 9. And then this will be where the remainder falls. But let me finish the verbiage in that statement on the previous page. You set up the division, long or synthetic, whichever one's most practical to do. The equation of the slanted asymptote is determined by the quotient of the division. You actually want to ignore the remainder. So this use of synthetic division is only to find the quotient, not to find the remainder. So, as a matter of fact, I don't care what's going to fall right there. I only need this part of the division. I just need the quotient to give me the end behavior for this particular rational function. So, let's do that division. Bring down the 1. Negative 2 times 1, negative 2. Those add up to negative 2. Those multiply to 4, but again, I don't care. That's going to be the remainder. The quotient is x plus or x minus 2. So what that means is the end behavior of this graph will be slanted, a slanted asymptote, and it will be y equals the quotient. Remember, don't just write the quotient down. Just writing x minus 2 is insufficient. You need your horizontal and slanted end behavior to be in the form of a lines equation. Y equals a constant for horizontal, and y equals mx plus b for slanted. So, this slanted asymptote will actually have a tilted effect on the ends of this graph. If we want to see what it looks like real quickly. So if I graph this function, x squared minus 9, x squared minus 9, divided by, parentheses around x plus 2, zoom standard. So there'll be a tilted end behavior to this line. Notice it doesn't have the horizontal behavior the first two have. It comes in at a tilt, and then it reaches its vertical asymptote at x equals negative 2. So there's the vertical asymptote jump. But then as it leaves the vertical asymptote's infinity jump, it continues to level off to the graph of this line. So just like I did last time, let me go ahead and overlap the graph of y equals x minus 2 here. So y equals x minus 2 is my slanted asymptote line. So when I overlap these graphs, you can see the blue graph, the rational graph, is really close to the slanted line here. The slanted line loses its influence on the graph because the vertical asymptote takes an effect in the middle. And then once you pass the vertical asymptote's infinity jump, the graph gets closer and closer to that slanted asymptote again. So that's why these are touted as dictating the end behavior of these graphs, because they can be used as graphing tools to help you, well, produce the image of what the graph should look like. Now, let's actually put this into practice and graph some rational functions.